Welcome to this lecture series. Today we will be starting the RF and microwave amplifier design. We have in the previous 10 lectures we have seen the filter design, microwave filter design. Now today we will start amplifier design. You know that signal amplification is one of the most basic needs of any electronic circuits, and at microwave region we are mainly concerned with power amplification. We generally are not so bothered about the voltage amplification as happens in low frequency or baseband cases. Here we are bothered about the power amplification because microwave power is at premium. It is very costly to produce microwave power. Also, we generally wirelessly transmit that power. So, we want sufficient power to get received at the receiver. That is why we take special care for microwave amplifier design. Also, you know that after World War II, when microwave sources like Kryston, travelling wave tube, magnetron, etc. were invented, that time the microwave amplifier were based on tubes, but with the advances in semiconductor technology, nowadays mainly transistor based amplifiers are used in microwave region, and already in earlier NPTEL courses we have seen the microwave sources, how those transistors, particularly the FET transistor, gas FETs, then HBT, HEMT, etc. are used. What are the design principles? Please refer there. Now, in this course, we will consider the transistor based amplifier as a black box, again as a two-port network, and we won't see the inner mechanism or the device mechanism of transistors that we have already seen earlier. Now, we will see a S parameter based description of that a transistor. So, with a two-port S parameterized transistor, we will try to design an amplifier and we will try to get power amplification by that. Now, if we compare the low frequency and high frequency power gains, we will see that at low frequency, you know that we generally describe the transistor with a H parameter, and most important parameter of that is HFE. So, generally that power gain at low frequency is something like this. This is generally HFE square. So, this HFE is the short circuit current gain. Now, generally the power gain becomes, if we express this in dB scale, then at 0 dB, that means 1, value of 1 power gain. So, it is 10. So, this frequency at which the AC short circuit current gain HFE, that falls to 1 HFE square, that is called the beta cutoff, the maximum usable frequency of the transistor, and there is also a relevant parameter called F beta, which is the frequency at which DC short circuit current gain beta of the transistor falls to 1. Ft is much higher than F beta, but if we go higher, we see that in microwave region this H parameter description is not adequate. There, as I said, that a whole transistor we represent by S parameter with an impedance level Z naught, characteristic impedance level Z naught, and if we see a typical power variation in the dB scale that takes the form of this, that generally this S21, if we take the pure transistor and if we try to find out that if we give some signal and out without any loading or proper matching, then this S21 square, that for certain region it is flat in dB scale, and then after that it generally falls off, generally with a roll off factor, and this frequency where the power gain becomes 1, that is called Fs, the frequency at which this power gain of the transistor alone, that falls to 1. However, by proper design we can have a, we can improve this, we can add some extra gain, and that actually will be the topic of this lecture series, that we can improve this part and make it go up to a more higher or up to a higher frequency F max. Now, this one we give a new name called GT max. This GT is called transducer power gain, and this maximum achievable thing is somewhat higher than S21 square. So, this is the play that a microwave engineer or an RF engineer who carefully designs an amplifier, he can get this much extra gain by proper designing, and also he can extend the frequency a bit to F max. So, this difference between Fs and F max, that allows, or an RF engineer should know how to exploit this gap, and so he can extend or push the amplifier design to a higher value. Obviously, below above this frequency no one will be willing to use this, because then the power gain that is falling to 1. So, this transducer power gain is a new quantity, or I will say that in microwave region we need to look carefully at various gain definitions, because here I am saying from the beginning of this course and all NPTEL courses that at high frequency or at microwave region we are very careful of the maximum power transfer, and we are very careful of the impedance matching. In one of the first NPTEL lectures for this microwave technology, we have elaborately said about impedance matching. Now, with when impedance matching is given its due importance, the in a microwave transistor based amplifier there are various power gains that are possible. So, we will go into that now, and for that we again assume that the transistor is represented by a 2-port network. This is the transistor block. Obviously, this is a microwave transistor. Generally, you know that HEMT or HBT, these transistors we can use up to 100 gigahertz. People are also trying to push it further. Now, this transistor for our purposes will be represented by its 2-port S parameters, and also we will assume that the characteristic impedance level of this transistor is at Z naught. Now, obviously, this one will be connecting with a source and a load. So, let us put a AC source here, and let us, that source will have typically an source resistance. Similarly, we will be connecting in this side this to a load, of load impedance ZL. Now you see that there are what happens to the waves here. So we can say that actually the terminal voltage here is V1, but actually we know that the at high frequency, actually at all frequency, but in high frequency we generally cannot neglect that actual signal propagation is in the form of waves. So there will be, you know, and for scattering parameter is defined in terms of that voltage waves. So we have an incident voltage wave going through here that we call V1 plus. Also depending on the mismatch, we know there will be a V1 minus here, and V1, the sum of these at this port 1, V1 plus plus V1 minus, that will be calling V1. Also we know that here the same thing will happen, that from this port there will be a incident voltage V2 plus that will be entering. Because of this, in general there will be mismatch here. So this V2 plus will come, and also there will be the V2 minus. Again this port voltage is nothing but V2 plus plus V2 minus. And also we will see that there will be various reflections. So if we look at the source side, we know if we look at here, we can see that there will be some source reflection. Similarly, if we look at here, there will be some input reflection, because input impedance will be seeing here, and depending on this impedance level there will be input reflection. Similarly, from here if we look, we can say that there will be a output reflection coefficient. Also from here if we look, there will be a load reflection coefficient. Now we know what are these values of this reflection coefficient. Let us see that this gamma s, the source reflection coefficient, that we know that will be given by Zs minus Z0 by Zs plus Z0, and this Zs is a complex number, Z0 is generally is a real number. So gamma s, it is a complex reflection coefficient because this is a complex number. Similarly, at the load side, due to mismatch between ZL and Z0, there will be ZL minus Z0 by ZL plus Z0. Now you see that I have certain power, depending on what is the input impedance I am seeing here, this Zs will be able to transfer a part of that power. We know that if Zs is chosen as Z in conjugate, then maximum power can be transferred to this transistor. Again here this transistor which is at impedance level Z0, it is seeing some output impedance. So depending on that, it will transfer a part of that power. If we can have a conjugate match here, then we know that it will be able to deliver that power, and then again depending on this output impedance and ZL, we can have a maximum power transfer here. But always we will not be able to do maximum power transfer. So that time some amount of power transfer will be there. So we define three definitions of power. You see here, with respect to this previous figure, we will say now three definitions of power. One is that power AVS, this is actually the power available from source. That means the power that the source can deliver, that we are calling power available from source. Similarly, we have here actually we are calling this transistor, it is a 2-port network. So, it is in the symbols, this will call as network. So, PAVN, this is power available from the output of network, which actually for the amplifier is this transistor part. Then also we have P, or before this I will say P in, where P in is power delivered at the input of the network S. Similarly, I will have PL, which is power delivered to load ZL. So, you see that I can now write 4 things. That means the power, input power is what power is going from here, then here it is taking P, sum of this power, because all power depending on the mismatch, all power cannot come. So, P AVS is the power that is available here, then again P AVN is the power that is available at the output, and again depending on the impedance level, the power that gets delivered is PL. So, there are these 4 different power things, which if everything is properly matched, then I know that, that means if I do conjugate matching from maximum power transfer theorem viewpoint, then I know whatever P in it is supplying, that maximum power will come here. That means generally that is for resistive loads half of this power, then again here due to this impedance level some of that will come here. From that again, if I can do maximum power transfer, maximum power will be transferred here. Now, based on this, then I have 3 definitions of power gain. You see that there are 3 definitions of power gain. The first one is called simple power gain. What is it? It is PL by P in. So, PL we know power delivered to load, and P in is the power delivered at the input of the network S, power delivered at the input of the network S. So, that means this G, if this is generally called G. So, G I can say, you see that G P in, power delivered at the input of network S. So, this is P in, this is my P AVS, power available from the source, this is P in. Please correct it, or again I am writing that this is my P AVS, this is my P in. Similarly, this is P AVN, power available from the network, this is PL. So, you see that when I am saying this, that means I am basically taking the power ratio, that how much power I could deliver to the load, but I am taking P in here, the input to the network. That means that I am not taking ZS level into consideration. So, I can say G is independent of ZS. Similarly, I can have the next one is called available power gain. it is generally denoted as GA, and this is P AVN by P AVS, where AVN and AVS are there. That means what I am seeing here, P AVN by P AVS. Here you see that I am considering power available here divided by this power. That means here now I have incorporated ZS, but I have not incorporated ZL. This loading I have not considered. So, I can say that GA is independent of ZL. So, obviously, this G is dependent on ZL, independent of ZS. This GA is dependent on ZS, independent of ZL. So, in both these definition you see I am keeping this open, that in one case I am not keeping considering the effect of ZS, in another case I am not considering the effect of ZL. So, obviously, I need another, because finally, my job is how much power I have in the source and how much I am delivering in the load. So, there will be a final one, which generally in low frequency we consider that, but here these powers depending on the impedance levels, they are not all equal. That is why we are doing this. This final power calculation is called transducer power gain, GT, a very important one, and it is defined as PL by PAVS. From the final PL by PAVS, I got this. So, this is the most important one, and you see I can write that GT is dependent on both ZS and ZL. So, when a complete loading is there, both in the load side and also the source impedance is considered, then what is my power gain? That is called transducer power gain. So, GTU is the most important factor, but you know that out of these three, obviously GT, that will be the least, because here after taking everything into account, this value will be reduced from any of these values, but these various parameters help us to have various separately consider various sides. Suppose if I want to find out that what is the effect on the gain of ZL, then I use this. What is the effect separately? If I want what is the effect on gain of ZS, I use this. When everything together, the final pudding is this one. Now, obviously, if everywhere the power is, the conjugate matching is there, that means input is conjugate matched, that means ZS equal to Z in star, also ZL is equal to Z out star, then I know that maximum power transfer is taking place. So, whatever is available, that I can deliver here as P in, and whatever P AVN is giving, that I can deliver to PL. So, under that condition, so we can write that when input and output are conjugately matched, all these definitions are same, G is equal to GA is equal to GT, but otherwise not, because for a GT is a function of ZS and ZL. So, for a particular selection of ZS and ZL only I get GT, a particular selection of ZS and ZL I get G, GA, etc. Now, these are in general different these power gains, but under conjugate matching I know that this will be maximized and that is called maximum power, and that time if we look at GT, that is the actual GT that you can get from a particular transistor power amplifier. Now, we want to find out what are the powers, because we have written this expression, but we need to make it gain etc. Finally, we need to convert to the device's parameters. So, here I can have any excitation Vs, but I need to find out an expression of these quantities Ga, G, G and Gt in terms of the parameters, S parameters of the transistor and also the load condition and source condition. It should be independent of the excitation that I give, because any voltage source I can change the voltage source, but the gain etc. they should not get changed. So, we will now need to manipulate and get some expression for these powers in terms of the source voltage Vs. So, that we will do. So, before that, first let us write what is our input impedance. If we look input reflection coefficient, see it here, I have input reflection coefficient here. Simply this reflection coefficient is nothing but V1 minus by V1 plus. So, I can write V1 minus by V1 plus, but this V1, this side is loaded. So, this V1 plus is entering, going from here as V2 minus, then coming back as V2 plus, again coming here as V1 minus. So, all these affects that. So, already in the first NPTEL lecture, basic building blocks or basic tools of microwave engineering, we have seen signal flow graph, and that time we have established that if I have a 2-port network and this reflection coefficient in the input, that can be easily expressed in terms of the S parameters of the 2-port network, and that becomes S11. Please refer there that how it is. It can be very simply from signal flow graph it can be derived. Also, please remember this, generally students, beginners, they make mistake that they think that input reflection coefficient that is always S11. No, it is S11 when you have this term that goes to 0, that means gamma L is 0. When gamma L is 0, gamma L 0 means output is matched. So, if port 2 is matched, then only I can say that input reflection coefficient is equal to S11. Otherwise, I will have to consider that what is the mismatch here, what is the load reflection coefficient, also S12 and S21 and S22 they matter. So, this we have earlier derived, and we know that this what is gamma in from impedance perspective, this is nothing but Z in minus Z naught by Z in plus Z naught. Now, also we know that what is the relation, because ultimately we will have to relate to the source voltage Vs. So, what is the relation between V1 and Vs? V1 is the terminal voltage. So, I can write that V1 is Vs into Z in by Z in plus Zs, simple voltage division. So, from this you just, since our actual quantities are V1 plus and V1 minus, so you express this V1 as V1 plus plus V1 minus, and with simple manipulation you will find out that I can write an expression for V1 plus in terms of Vs as this, also incorporate what is gamma S. I have already written gamma S here. So, in terms of Vs and gamma S we can do it, it is simple manipulation. So, if I have this, that what is the input power, you see what is my P in. P in is that whatever V1 plus this voltage wave is carrying how much power? Average power if we assume, then P in I can write as half Z naught V 1 plus square into 1 minus gamma in square. This we have earlier seen how to do this. P in is this, we know impedance level is Z naught and there is a reflection here. So, if we subtract that reflected power, we know how much power is being inputted to this network. So, P in is this. Now, with V 1 finally we want to, because V 1 plus it will change from various loading condition, but V s it is a source voltage that is independent of all this. So, let us relate it there, and if we do that, that means if we put this expression of V 1 plus, we get the expression of V s square by 8 Z naught 1 minus gamma s square by 1 minus gamma s gamma in square into 1 minus gamma in square. So, this is an important relation. P in is this, finally we got it, that this is an expression of P in. Also, I need to find the other two expressions, that what is P A V s, what is P A V n, what is P L. So, I have done P in. Now, also what will be P L? Let us see P L. So, P L can I write from this? What will be P L? You see what V 2 minus is going to P L. So, I can write P L as V 2 minus square by 2 Z naught 1 minus gamma L square, and then I can V 2 minus, here I have done for V 1 minus, V 2 minus also we can relate with this gamma s and gamma L. So, this finally if we do, we can write that this will also turn out to be V s square by 8 Z naught s to 1 square into 1 minus gamma L square into 1 minus gamma s square divided by 1 minus s to 2 gamma L square to 1 minus gamma s gamma in square. So, we have got P L in terms of V s square, and all these are S parameters, and gamma s and gamma L and gamma in. Similarly, now let us see the other two available things. What is P available S? That is the power that the source can make available. So, this is source can make available maximum power under when this input side is conjugate matched. That means, P A V s is that power. So, I can say P A V s is power P in when Z in is chosen as Z s star. So, I already have P in expression. You see, I already have P in expression. There I should enforce this condition that Z in is equal to Z s star. Z in is equal to Z s star means gamma in is equal to gamma s star. So, if I put it here, I get the expression of P A V s, that is V s square 1 minus gamma s square by 8 Z naught 1 minus gamma S square. Similarly, what is P AVN? P AVN is the maximum power that can be transferred to the load. So, available from this network, and that can be transferred to the load when this side is conjugately matched. So, again I have PL expression, there I will have to put the conjugate matching. So, I can say P AVN is power PL when ZL is equal to Z out star. That means this implies that gamma out is equal to gamma L star. So, I can, if I do that, then I get the expression of P AVN, and that becomes P S square by 8 Z naught S 21 square 1 minus gamma out square into 1 minus gamma S square divided by 1 minus S22 gamma out star square into 1 minus gamma S gamma in square. So, I have these expressions. So, all 4 power quantities we have expressed in terms of source voltage, the impedance level of the active device, that means transistor, then S parameter of transistor, and various reflection coefficients depending on the load and source conditions. So, we are in a position to find out analytical expressions for various gain quantities that we will see in the next lecture. Thank you.